Okay, so welcome again. So today we are doing two lectures for the course AI and Cryptography. We have just one set of slides, so it will just be broken between this morning session and the afternoon session. And it is about, if you remember the timetable that I showed yesterday, the use of artificial intelligence methods to design cryptographic primitives, in particular symmetric cryptographic primitives, and not public key primitives that we saw at the end of yesterday's lecture. So the main topics for today are, of course, will be broken in two parts, but we will start with an introduction of Boolean functions and Sboxes for symmetric cryptography. We already mentioned Sboxes yesterday for the substitution permutation network, which is a model of block ciphers, and also the kind of properties of security properties that they need to satisfy when used inside these cryptographic algorithms. And then we will see that these properties can be defined in terms of combinatorial optimization. So they can be cast as a combinatorial optimization problem where you need to maximize a certain criteria or minimize other. And so you can use artificial intelligence methods, in particular those pertaining to search and optimization, like evolutionary algorithms and genetic algorithms, to optimize these fitness functions, basically. Then we will show also that Sboxes can be, let's say, also evolved through evolutionary algorithms using a specific model that also is studied in the domain of artificial intelligence, that is cellular automata. So cellular automata are a model for discrete complex systems in particular. And then we will move to other representations that we, different from those that we see in the first part. So the use of orthogonal arrays are kind of combinatorial objects that will be, let's say, used to define in a different way certain properties of Boolean functions. And finally, let's say the most interesting, at least in my opinion, topic, which is the use of evolutionary algorithms or AI optimization methods to evolve what are called algebraic constructions. So what is usually done by human mathematicians, we will see how genetic programming in particular can also obtain, let's say. The references are mainly these three that I listed here. So this book by Claude Carlet, and two survey papers that were co-authored by me and another set of co-authors. You can see all the references in the end. Okay, so let's start. We start first with Boolean functions and Sboxes. So if you remember yesterday, we said that in stream ciphers, so where we have a symmetric encryption algorithm where each symbol, each bit is encrypted with one symbol or one bit of the key, so one at a time, we need a pseudorandom generator because the Vernam stream cipher, the original one, that was the one-time pad, basically, where you had a key that was as long as the plaintext, is too inconvenient to use because we need to generate a lot of random bits and they are not, let's say, very cheap to come by in nature. So what we do is to use a pseudorandom generator, which is a deterministic algorithm, this PRG block here that you see here in the diagram. And this will stretch like a short secret key that we put into input, and it is shared between Alice and Bob. So they shared it in a, let's say, in the beginning, before the protocol takes place. So for example, using Diffie-Hellman key agreement or some public key protocol like that. And then the output of this pseudorandom generator will be a key stream Z that will be XORed bit by bit with the plaintext PT. And likewise for decryption, the ciphertext will be XORed with the same key stream that is generated by Bob, starting from the same secret key, in order to obtain the original plaintext. Now, the question is how to build a pseudo-random generator in practice. We saw yesterday some theoretical characterization that was very strong using one-way functions, but actually now we are asking something more concrete. So how do we build one in practice? And historically, let's say that among the first models of pseudo-random generators that were used also for cryptography was this linear feedback shift register, where you have like a device like this. So you can see here in the diagram, these square blocks, D0, D1 up to dk minus 1 are basically flip-flops. And these flip-flops are containing the state of your pseudorandom generator. So they are bit either 0 or 1. And they are like connected in this fashion. So at each clock cycle, they shift their value to the right. And the last one, of course, will give like the next output bit for the key stream. And then you see that there is also this feedback that it is coming from all flip-flops that are multiplied with a constant, like a coefficient a0, a1, etc., up to ak minus 1. And we do a linear combination of their values with these coefficients, which is fed back to the rightmost flip-flops. So we have these continuous linear recurring sequences that can generate an infinite sequence. Of course, since we have a finite width for our register, for our flip-flops, so we have k of them, after at most 2 to the power of k clock cycle, we will see like the pseudo-random key stream to be, that will start to repeat itself. But at least this is okay in the sense that you say, okay, you take like a large enough register, and then you say, okay, it will start to repeat like after a very long time. The problem is that even in this way, this pseudo-random generator is quite weak, because if you have at least, if the adversary, so Eve, knows at least 2k consecutive bits of the key stream, then she can recover the initialization of the linear feedback shift register by leveraging the linearity of this machine. And how do you do this? So this is done with what we called KPA in the first lecture. So known plain text attack. So basically, suppose that Eve knows for some reason a stream of plain text, so we call it x1, x2 until x began, and also the corresponding cipher text. So this is plain text, and the corresponding cipher text y1, y2 until y began. This will be the cipher text. So this is the setting of our known plain text attack. So we know pair plain text and corresponding cipher text without knowing the encryption key, which in this case would be the initialization of the linear feedback shift register. So the first values that we put inside the flip-flops. And now basically from here, what she can do, since she knows what is the encryption operation, so it's a Vernam-like cipher, so we are XORing, she can reconstruct also the piece of key stream Z. So this will be Z1, Z2 until Z began, and she will do it by computing bit by bit XOR between these two things here, because we know that the encryption function would be xi XOR zi, and this will be yi. So we just move this in this part, and we will get zi equal to yi XOR xi. So we have here z1, which will be x1 XOR y1, etc., etc. Okay, so she can reconstruct this part of the key stream. Now, what happened when big N, so the number of bits that Eve was able to discover of the key stream, is greater than or equal to 2 times k, so twice the size of our linear feedback shift register. Well, at this point, basically what we have is a set of k linear equations in k unknowns. So we assume also that Eve knows what is the weight of this linear feedback shift register in this attack. So basically what she needs to do is to consider this equation in matrix form. Let's see, where is, okay, eraser. So write it here. So we will have that after the first k clock cycles, in particular, we will have this relation here. So zk plus 1, zk plus 2 until z2k, so this is a vector, is equal to, let us assume for the time being that that first coefficient that you see there in the slide, so a, that is like a constant term, is 0. It doesn't change that much. So we can safely assume that it is equal to 0. So we will have our coefficient put into a vector, a0, a1, until ak minus 1, multiplied by what? Okay, here I need to go, sorry, on the other new line, but the multiplication of this vector here by a matrix that has this form. So we have z1, z2 until zk, so the first k bit of the key stream that she recovered. Then we shift, because we know how it works with this key stream. It is obtained by shifting every time one place to the left the values inside the flip-flops. So the next column will be computed by starting from z2, then we have z3, and we arrive until zk plus 1. So we shifted one place to the right, and then we continue like this until we arrive at zk plus 1 until z2k minus 1. So this will be the linear relation that she knows, because she knows how what is the model that is being used. She doesn't know these coefficients here. These are what are needed in order to reconstruct the whole key stream, basically. So the idea basically is just to retrieve this vector here by shifting, let's say, putting this on the left, or let's say just keeping this here, multiplying this vector by the inverse of this matrix. So it's very simple. In the end, we can just say, let's say, do it here. So very quickly, this will be a0, ak minus 1, which will be equal to zk plus 1 until z2k by z1, zk, z2k minus 1 to the minus 1, so the inverse matrix. So basically, this is too weak in order to do some secure pseudo-random generation for our Vernam-like stream cipher. So what we need to do is to come up with something more complicated. And this more complicated thing, for example, could be what is called the combiner model. So this is a model for pseudo-random generators that nowadays is not used that much anymore, but it is still like useful in order to understand how Boolean functions play a role in the construction of this pseudo-random generation. So we will stick with this. Then there are, if you look into the references, in particular Claude Carlet books, you will see that there are many other more secure models, such as the filter model. But for the time being, we use the combiner model. So the combiner model is quite simple. Instead of having a single linear feedback shift register, we will have n linear feedback shift register, and we clock them together in parallel. So at each clock cycle, we will receive n input bits. And now these n input bits, so x1, x2 until xn, they are not given directly to the user for encryption to do the key stream generate as a key stream, but we combine them using this function f, which is called a combiner function, f computed over x1 up to xn, and the output of this will be the next bit in our keystream, in our pseudorandom keystream. The nice thing about this model is that we can reduce basically the security of these pseudorandom generators by looking at the cryptographic properties of the Boolean function f. So this function f is something that is mapping n bit streams to a single output bit. So this is the reason why now we are going to see a bit more about the cryptographic properties of Boolean functions. So Boolean functions, okay, are very basic combinatorial objects used in computer science, and the most basic form to represent them is to use a truth table, right? So assume that we have our n-bit vectors. So for example, n is equal to 3 in our example, and we fix an order over them, for example, the lexicographic order. So we start from 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0. Here I'm using the least significant bit first order. So the least significant bit is listed first. And for each of them, for each of these vectors ordered lexicographically, we put the corresponding output bit. That can be whatever we want. So we have 2 to the power of n outputs to determine. And it means that the truth table, once the order has been set, can be represented by just this single string that I called omega f in the slide. So 2 to the power of n bit vector that is specifying the output of this function for each possible input vector. So this is very basic. A second common representation that is used in cryptography and coding theory for Boolean function is the so-called algebraic normal form. So this is basically a sum where the sum is an XOR of products, where the products are AND. So the idea is that here we are considering the set 0, 1 as a finite field. So it is usually denoted with this symbol here. And it means in particular that we are having 2 operations. So sum will be the XOR, which is denoted like this. And the AND will be logical AND. Sorry, the multiplication will be, so MLT will be the AND, or simply the multiplication of 2 bits. It's the same thing. So this is a finite field, so it satisfies all the x's of a finite field. And in particular, we will endow, let's say, we will consider the set of 2 to the power of n bit vectors. We will denote it like this, so f2 to the n. And this f2 to the n is endowed with the structure of a vector space. So these vectors here are not just bit strings, but are really vectors in the linear algebra sense, so vector space, where the sum of vectors is simply the bitwise XOR between 2 vectors, and the multiplication by a scalar is the multiplication by a single bit with the logical AND. So with this machinery here, now we can define like the algebraic normal form in this way, like on the slide. So the corresponding algebraic normal form of this function that you see in the truth table defined in that way is the following one. So you have like x1, XOR x2, XOR x3, so the sum of the 3 bits in the input, plus the AND of the second and the third bit. So this is very simple, but in any case, the important thing is that this algebraic normal form is a unique representation of any Boolean function. So for each Boolean function, you have only one algebraic normal form. And there is like what is called the Möbius transform in order to go from the truth table to the algebraic normal form and back, but it's not important, let's say here. A bit more important is to see the Walsh transform, which is a third representation of Boolean functions. And it is quite, let's say, important in the sense that a lot of cryptographic properties of Boolean functions can be expressed in terms of the Walsh transform. So the Walsh transform is basically a kind of discrete Fourier transform, where instead of using the usual orthonormal basis of trigonometric functions, you are using different bases, the so-called basis of Walsh functions, where you have a set of square wave functions, let's say. Basically, from a mathematical point of view, they're just +1 or -1, basically, this function here. So they are some functions with this kind of shape. So you have -1 until 0, and then you go up here and you have +1. So here is -1, and when you arrive at 0, it will become +1. So you have these kind of functions that defines the basis for this transformation. And basically what we are doing here with this Walsh transform is to measure what is the correlation between our function and the set of all linear functions. What are linear functions? Linear functions are basically those where you can see in the algebraic normal form that the degree is at most 1. So we have, for example, this is not linear, what you see here, because we have this multiplication of x2 and x3, but if we didn't have that x2 by x3, then that would be a linear function. So the Walsh transform, basically you see here that is taking as an argument the function itself, f, and a vector a that is defining a linear combination of the input variables. So it means that this writing here is to be intended as a scalar product. So it will be the classic dot product that is done in this way. So if we have a that is a1, a2 up to an, and x that is x1 up to xn, then we will have a1 and x1 XOR a2 and x2 XOR until an and xn. So this basically defines you, depending on the values of the coefficient vector a, defines a linear function, because only the coordinates that are set to 1 in this vector a will select basically the input variables that we are XORing together to get our linear function. So here what you see in this formula, it's basically this sum over all possible vectors x of this correlation here that is not like, it's done in the bipolar domain, so in -1 and +1. That is the reason why we are computing -1 to the power of this exponent. And then we do the XOR of the value of the function computed over that particular input x and the scalar product of a dot x. And this we do for all possible a, so for all possible 2 to the power of n linear functions. And this is an example of the Walsh transform that we get from these particular functions that we put in our example. So you will see here that for the linear function that is defined by the vector 0, 0, 0, so the now function, basically, the constant function 0, we will have 0 as a coefficient of our Walsh transform. If we compute it for a equal to 1, 0, 0, we will have -4. For 0, 1, 0, we will have again 0. For 1, 1, 0, 4, +4, and so on for all the others. Okay, so now that we have under our belt this,
yeah, this you can recover f from the word.
Yes, we can also do, yeah, we can also like do
some inverse.
Exactly. Yeah, precisely. We can also apply what is called the inverse Walsh transform, what you do also with the inverse Fourier transform. Mm-hmm. So basically you can, so the problem with the Walsh transform is that contrarily to the algebraic normal form is not a unique representation because of Boolean functions, because you have something that is mapping from the Walsh transform is mapping from f2 to the f2 to the 2 to the n, basically. So we have our description of a single function, let's say in terms of its truth table, not to the same set, but to z to the 2 to the n. So this function here is actually injective. So it means that it's still a unique representation in the sense that we don't have two different Boolean functions that ends up with the same Walsh profile, Walsh spectrum. But on the other hand, if you take like this any spectrum from here and you go back by applying this inverse Walsh transform, in general, you don't get a Boolean function. You get what is called a pseudo-Boolean function, which actually I think that Luigi is remembered for his work that we did together a bit of time ago. But anyway, yes, you can. The bottom line is that you can recover if you have the Walsh spectrum of a Boolean function. You can go back using the inverse Walsh transform. Okay. Now let's go with our cryptographic properties and how to characterize them using these representations that we saw. So the first one is balancedness. That is very important in cryptography. So we start by saying that what is called the Hamming weight of a Boolean function, which is basically the number of ones that we see in the truth table of the function. So the vector omega f that we saw in the previous slide. So like here, we will have, well, we had also here, we had like 8 bits in total because there are 3 input variables. So 2 to the power of 3 combination, 8. And the number of ones is 4. So we have Hamming weight equal to 4. And we say that f is balanced is this if its Hamming weight is precisely half of the length of this vector. So we have an equal number of zeros and ones. So this function in our example is balanced because we have 4 out of 8 bits that are set to 1. The Walsh characterization of this property is very simple because we just need to compute the, well, this is a small typo that we have here. I was using a different notation instead of f hat, we were using wf. But anyway, the idea is that you just need to compute the Walsh transform over the null vector 0. And the idea is that when you set to 0 this, basically you're only summing for all possible inputs, you are summing the value of the function f of x. So this is the reason why if you get 0 here, it means that you have an equal number of -1 and an equal number of +1, so they cancel each other out. So this is the reason why you get 0 there. So it is balanced if and only if it's bidirectional, this implication, you have 0 in the null vector. And this is important because if you have an unbalanced combiner function in the combiner model, then it's quite easy to mount what we called yesterday a distinguishing attack. So the attacker, Eve, has a non-negligible probability of saying, okay, I can distinguish between an encryption of 0 and then an encryption of 1 because we know that the output of this function is biased. So the second one is the algebraic degree, which we kind of already defined before. It's basically the degree of the polynomial that is defining the algebraic normal form. So here we have, for example, in this A and F that is different from the previous example, we have x1 by x2 plus x1 plus x2 plus x3. So the degree will be 2 in this case because, well, we have this monomial here that has degree 2 because it is multiplying 2 different variables. So linear functions, like we said, are those that have degree 1 instead. And again, we want the algebraic degree of a combiner function in the combiner model to be as high as possible because this is basically gives a resistance to what is called a Berlekamp-Massey attack that is able to recover, let's say, the initialization of the n linear feedback shift register that we had in our combiner model. So if the degree is too low, then we can apply this attack quite efficiently. If it is high, it is still possible to apply it, but the computational complexity becomes quite high, so it is not feasible anymore at a certain point. And then we have nonlinearity. So the problem, like we said, with the linear feedback shift register is that they are linear, right? So we can use linear algebra in order to recover the initialization of the linear feedback shift register and thus break completely the crypto system. So we want our function to be nonlinear, and what does it mean? Well, we defined the linear functions as those that have degree 1 with their algebraic normal form. And in that sense, basically, if we consider the set of all possible linear functions in terms of their truth table vectors, okay, and then we take our function f, of which we want to compute the nonlinearity, then basically the nonlinearity of f will be the minimum Hamming distance of f from the set of all possible linear functions. So for each possible linear functions, I don't know, now I'm just inventing, let's say, in a certain sense. I don't know if these are really linear or not, but anyway, just to give you an idea. So we will have 1, 0, 0, 1, 0, 0. We will have 2 to the n linear functions. And then for each of them, we compute, let's say, the Hamming distance of the truth table of our function, which in this case is 0, 1, 1, 1, 1, 0, 0, 0. So here, for example, we will have a Hamming distance of this is okay, this is okay, this is okay. Here we have a difference, so we have 1. Here we have 1, so it's okay. Here we have a 0, and the last one is still another mismatch. So the Hamming distance between these two will be 2 in particular. And then we do it for all others, and we take the minimum. So this will be the minimum distance, and we call this the nonlinearity. This can be also characterized through the Walsh transform quite easily using that particular formula. So basically we are employing the coefficient, the Walsh coefficient of the highest magnitude in absolute value. Why? Because basically we said that each coefficient is computing the correlation between our function and a particular linear function. So if we take like the highly correlated possible function, then we also get, let's say, the Hamming distance or the minimum Hamming distance in this way. And so basically here you compute the nonlinearity in this way. So we have the maximum magnitude is 4 because we have minus 4, 4, 4, 4, and just 0. So the nonlinearity in this case will be 2 for our function. And again, functions need to have like high nonlinearity when used in the combiner model because they can resist what is called the fast correlation attacks. So if we have a nonlinearity that is too low, it means that we can approximate this function with a linear function. And with that, we can try to predict what will be the next bit, basically. Okay, now just an excursion about bent functions. So bent functions are basically, let's say, the best possible that we can get with respect to nonlinearity. So the fact is that for any Boolean function, we have what is called Parseval's relation. And this is, let's say, a relation that is quite general in harmonic analysis, actually. So it is an instance of a more general phenomenon. And the idea is that when you do it, for example, with the Fourier transform, it means that if you do the integral of the squared Fourier spectrum, then this will be constant, basically. Here we have something similar, except that we are summing instead of integrating, because we are in a discrete setting. And we are summing the whole spectrum squared again. And the value here will always be 2 to the power of 2n. This for any Boolean function is valid. And this tells you what? It tells you that if you want to find the best possible nonlinearity, and you have that constraint of Parseval relation, then you can reason by following these arguments. So let's say that you have your spectrum, let's say. So here you will have 0, 0, 0, 1, 0, 0, etc., up to 1, 1, 1. Okay, and then you have, let's say, a big file, a big stack of blocks that has a height of 2 to the power of 2n. So the value that you find in the Parseval relation. And then you say, okay, basically what I want to do is to distribute this file over this spectrum in such a way that it is the, let's say, the flattest possible. Yeah, exactly. So this happens basically if everything has in absolute value the same height. So it will have something like this, and maybe we can have something like this, and then we can have something like this. Then we can have something. So the sign is not important, but ideally we want to have everything of the same height, okay? And this height will be what? Well, basically you need to compute the square root of that value here of this pi, so to the power of 2n, and you get as a coefficient for each possible linear function of, say, in absolute value 2 to the power of n divided by 2. So this is what you get if you distribute in the flattest possible way. What is the problem here? The problem is that we said that the Walsh transform is giving us always integer numbers. And here we have a coefficient that has something with a fractional exponent. So basically, this is okay only if n is even. Okay, assume that we have n even. If we find a Boolean function of this kind, then we call it a band function. And this, by construction, will have the highest possible nonlinearity. Why? Because all of them have all the coefficients have the same smallest possible value, which is 2 to the power of n divided by 2, because of Parseval's relation. And so they have the highest possible nonlinearity. But now what is the problem? So you see now how it starts to get complicated with various trade-offs. We want also balancedness, we said in the beginning. And the problem is that now we have all of these coefficients that are equal to either plus or minus 2 to the power of n divided by 2, included this one. And this one, we said in the beginning, that is characterizing the balancedness of our function. So since it is not 0 here, it means that band functions cannot be balanced. So we cannot use them directly as combiner functions in our stream ciphers. So this is the problem, basically. They exist only when n is even, and moreover, they're also unbalanced. And okay, here you can see an example with 4 variables over the slide. Okay, next, another property is the property of resiliency, or also correlation immunity. So basically, resiliency means that if we fix any subset of t variables, where t is ranging between 0 and n, where n is the number of input variables, then the restriction of f by fixing these t variables are always balanced. And something similar is done with what is called correlation immunity, which we will see a bit better this afternoon, where basically you have that by fixing at most t variables, then instead of having the restrictions that have the same, that are always balanced, basically, they will have all the same Hamming weight in their truth table. But okay, for the moment, let's stick with resiliency. So resiliency is easy to characterize with Walsh transform because it is similar to balancedness. As a matter of fact, if you set t to 0, you get exactly balancedness. Why? Because these, when you fix t variables, it means that you need to consider in the truth table all the vectors that have Hamming weight at most t. So when you are considering t equal to 0, it means that you are considering only one vector, the null vector that has Hamming weight 0. So it doesn't have any 1. And it means that that is the null coefficient of the Walsh transform, and if it is 0, then it means that the function is balanced. So basically, 0 resiliency corresponds to balancedness. And T resiliency for T that is strictly greater than 0 is T resiliency. So in this case, we have something that in this example is not even one resilient, because if you see here this vector, this coefficient here over 0, 0, 1, it's -4, and so it is not, it's different from 0, and it means that the function is failing the criterion of one resilience in this case. In general, we would like to have functions that are resilient of a high order, because this allows to resist what are called correlation attacks over the linear feedback shift registers. And okay, so this basically closes the part over the cryptographic properties of Boolean functions. Now, do you have any questions, first of all? Yeah?
I have a brief confirmation on the combiner model.
Yeah.
So we have several linear feedback shift registers.
Yes.
I guess each of them has a different set of coefficients.
Yes, it is. They are initialized with different sets of coefficients, and
but the seed, which is the key, it's at step 0 is the same for each linear feedback shift register.
Yeah, you can have it in both ways. You can have it both that they are initialized with the same seed, or also you can have like a larger seed and then chop it up in smaller, depending on the size of these linear feedback shift registers. So you have both possibilities in that way.
Fine.
Good. Other questions over the chat? You see anything, Luca? Or okay. Then I guess that we can move on. So we finish earlier, not like yesterday. So, okay, we arrived so far with Boolean functions that we said are functions that are mapping n-bit vectors to a single output vector. Now we are moving to Sboxes that we already introduced yesterday when we talked about block ciphers and how they are used inside the substitution permutation network paradigm for block ciphers. So basically an Sbox is what? Is just the vectorization or the vectorized version of a Boolean function. Instead of having a single output value, we will have n of them. So in particular in substitution permutation networks, we want Sboxes, so vectorial Boolean functions, where the number of input bits is equal to the number of output bits. This is because we want to be able to do also decryption, so we need everything to be bijective, basically. And if they don't have the same number of inputs and outputs, of course, bijectivity is not achievable. So in general, you can have vectorial Boolean functions of n inputs and m outputs. But let's say that for the most part, we will focus over the case n and n in input and n in output. And okay, for the general definition, of course, we consider, let's say, in the notation just n and m. So we call an Sbox with n inputs and m outputs an nm function. And this can be basically defined by what? By m coordinate functions. So we have again our representation in terms of a truth table. Okay. So we have in this example like n, which is equal to m, which is equal to 3. So it's a 3 by 3 bit Sbox, which is called the three-way Sbox because it was used in a cipher invented by Johan Damon called three-way. And the idea is that you have again your input vectors that are fixed in lexicographic order. And for each output coordinate, you have basically a Boolean function. So for the first coordinate, so the leftmost one in our output, we will have a coordinate function called f1, which is acting on the whole input x1, x2, x3. For the central coordinate, we have a second coordinate function f2, which is again acting on the whole input, and the same also for the third coordinate. So we can have either a matrix representation of our truth table for an Sbox, or we can have like a more compact representation by using the decimal representation of these binary vectors. So here we have, instead of 0, 0, 0, 0, 0, 1, etc. for the input vectors, we have the integer numbers from 0 up to 7. And then we have the corresponding outputs, which would be what is determined by the output of the three-way Sboxes, so 0, 5, 6, etc. So Sboxes are defined in terms of coordinate functions, which are still Boolean functions, and we saw before how to analyze them. Another important property of Sboxes are component functions, because these are used to define their cryptographic properties. So component functions are basically linear combinations of coordinate functions. So it's quite simple, the idea. Instead of considering a single coordinate function, which is a Boolean function, we consider a combination of two, or let's say even one of them, depends, in that way it would be still a coordinate function, but basically we are computing the XOR of different coordinate functions. Like in this example, we have this vector v that is 1, 0, 1, 0, 1, 0. So we only select the coordinates that are set to 1 in this vector, and we sum them together. So here, if we have 6 coordinates, f1, f2, up to f6, we are just summing together f1, f3, and f5, and this would be a component function. So in total, we have, again, 2 to the power of n components, because we can select, well, sorry, this would be 2 to the m in general, because it is the number of outputs, right? But then we said that m would be equal to n in our cases. So 2 to the m components. Usually you say 2 to the m minus 1 because you don't want to consider the trivial component that is not summing anything. But in general, it's an exponential number of components that we have. So the Walsh-Hadamard transform at this point is very simple, in the sense that, well, it is more complicated, as you can see from this table, but it is very simple. We just compute the Walsh transform for each possible component. So basically, instead of having a single line with a single Walsh spectrum, we will have 2 to the power of n in total, 2 to the power of n in total Walsh spectra, one for each component. But the, let's say, the formula, as you can see, is always the same, so it is not changing anything. So this is the Walsh spectrum from the whole Sbox of three-way. Balancedness now is basically defined if you have the generic case of n inputs and m outputs as something where you have like balanced preimages, in the sense that if you take like any output vector y, then the number of preimages that are mapping to that particular output vector needs to be always the same number. So 2 to the power of n minus m. What does it mean? It means that when you are considering n equal to m, then basically what you get is bijectivity, because you will have 2 to the power of n minus n. So 2 to the 0, which is 1, which is that any preimage need to have exactly one preimage, which is exactly one of the definition of bijectivity. So the three-way Sbox is bijective, in the sense that you can see that it is a permutation or a bijective function here. Well, maybe not directly from here, but if you see from the decimal representation on this slide, you can see that the decimal output is a permutation of the input. So this is another way of seeing bijectivity. And okay, so balancedness. Nonlinearity, it's also quite similar to the case of Boolean functions, because basically we are just computing the Walsh-Hadamard transform of all components, and then we take what is the minimum nonlinearity among all possible non-trivial components. So in this case, we are excluding the null vector, because that would be trivial actually if you compute the Walsh transform in that case. So we compute the nonlinearity using the same formula for Boolean function for each component of our Sbox, and then we take the minimum. And this minimum will be the nonlinearity of the whole Sbox. So the nonlinearity is basically computed in the worst case. If you have even only one component, for example, in your Sbox that is linear, that has nonlinearity 0, then it is considered to be completely linear, the whole Sbox, even if it has all other components that are nonlinear. Actually, you see that when the number of linear components also form like a subspace, a vector subspace. So if you have, for example, 2 linear components inside your Sbox, then you do also the linear combination between these 2, and you get in total 4 components, and so on. So you have a vector space structure. So you cannot have, for example, something like, 5 components. You need to have like a power of 2, basically, in the space of linear components. So this is an example with the 3-way Sbox. So the nonlinearity will be 2, because basically it is quite uniform. In this case, we are getting 2 for each possible non-trivial component. And finally, the less important property for Sboxes is what is called differential uniformity. So nonlinearity basically before had a similar role than we saw before with the Boolean function. So for Sboxes, basically the problem is that if you have an Sbox with a low nonlinearity, then you can do an attack called the linear cryptanalysis in an efficient way. Differential uniformity instead is something where you want to have as low as possible, because if it is not as low as possible, then you can do another kind of attack, which is called differential cryptanalysis. And the idea is that basically you are going to consider like the differences between 2 vectors, 2 input vectors, and the differences between the corresponding output vectors after you have computed them through the Sbox. So how do you formalize this property? You define this, what is called the delta difference table. So you get 2 vectors, one input vector A, which is no 0, so we are excluding the null vector, and an output vector B, which can be anything. And then you compute this set here, which is the set of all input vectors, X, such that if you consider this dA f of x is equal to b. What is dA of f of x? So it is called the derivative in the direction of, is the razor? The derivative in the direction determined by a. So we don't have derivatives as in the case of real analysis, for example, here, because we are working over a finite discrete space. But we can have some surrogate derivative. So here the idea would be that
the algebraic structure, like we do for polynomials, something like that, that kind of differential.
Well, not really, because I don't know if I got correctly what you mean, but with polynomials, yes, you can also define formal derivatives. You use the same rules. Now here you're using something like derivative in the sense of differences. So this would be dA of f of x would be something like f of x XOR f of x XOR a. So we are computing, so this, since the sum in f2 is basically the same as difference, you can consider this as a difference basically. So we are computing the XOR between the original vector x and the vector that is shifted a bit by a. So this would be the formal derivative of Boolean functions. Derivative with respect to vector a. So we are computing all derivatives, and we group all the derivatives that are equal to the output vector b that we selected. So we construct this for all possible combinations of a and b, and we get the so-called delta difference table. And now if we get, like for each of these sets, delta f of AB the corresponding cardinality. We call this small delta f of A and B. Then we can define the differential uniformity as the maximum over all possible cardinalities of these delta difference tables. So this is to give you an idea that maybe is a bit clearer with this example. So we have again our three-way S-box. So we compute for each possible combinations of A and B that we consider the cardinalities of the corresponding set delta of AB. And then we will have, let's say, a set of a matrix of numbers, and we get the highest possible numbers inside this matrix. So here again, we only have either 0 or 2. So the differential uniformity will be 2. Actually, 2 is the minimum possible that you can do in any S-box. So it's the best that you can hope for. And if you are in this situation, like in the example of this three-way S-box, then you call this an APN function or an almost perfect nonlinear function. The reason why it is called almost perfect nonlinear is related to the fact that differential uniformity also has relations to nonlinearity, but we are not going to see these kind of details just as for the sake of completeness. So it's just the way you call like the optimal S-boxes in this way. Now, what is the problem? The problem is that basically we have trade-offs between all these properties that we overviewed in the course of this lecture. First of all, we have for the case of Boolean functions, so not S-boxes, but let's say single output Boolean functions, we have the covering radius bound, which is related to Parseval relations that we saw before. So basically, that bound there is saying that the best that you can do with nonlinearity is having the nonlinearity of a band function, which of course can occur only if n is even. So this is a general trade-off just on nonlinearity. Why it is called covering radius bound? Well, because it has a coding theoretic justification. So in coding theory, you can study what are called the Reed-Muller codes, which are basically the codes where the code words are the truth tables of Boolean functions. And in particular, if you take the Reed-Muller code of order 1, then you have basically all the code words that are linear functions. So it's the set of all linear functions. And since you have, let's say, in your space, like all these linear functions, in a certain sense, you know that, or I don't know if you have any classes or courses or on coding theory, but anyway, the idea is that you want to spread your code words as far as possible in such a way that their distances is the highest possible. So you have a minimum Hamming distance between them that is as large as possible. And by doing this, basically, the covering radius would be, let's say, if you have like distance between any two code words, that is something like this, the covering radius would be the radius of these spheres inside this space. So this is the reason why it is called covering radius bound. So basically, it means that the band functions, so the optimal functions from nonlinearity, are lying, let's say, over the edges, over the surfaces of these spheres. Then we have Siegenthaler's bound. This is related to the algebraic degree and the resiliency order of a Boolean function. So basically we have that the degree must be less than or equal than the number of variables minus the order of resiliency minus 1. So the greater is the degree, the lower must be the resiliency order, and vice versa. And then Tarannikov's bound, which is actually a consequence of Sarkar-Mitra's bound, is relating the nonlinearity to the order of resiliency. So the nonlinearity must be at most 2 to the power of n minus 1 minus 2 to the power of t plus 1. So again, it means that the more you have a function that is nonlinear, the less it is resilient in a certain sense. Besides these trade-offs, this constraint that we need to consider when selecting a Boolean function, we also are facing the problem that the number of Boolean functions is quite huge because it is super exponential in the number of variables. So we have our truth table that is already something like 0, 0 up to 1, 1, 1. So here in the output row of the table, we have 2 to the power of n possible bits to set, and each of them can be either a 0 or a 1. So in total, we will have 2 to the power of 2 to the power of n, which means that basically you can do exhaustive search to find the best possible Boolean function satisfying all those trade-offs, only up to, let's say, 5 variables, because there are like 4 billions and something, so you can do it quite easily in a matter of a few hours, even with your own laptop. Already for 6 variables, it becomes very tricky to do exhaustive search. And then for 8 variables, for example, which is kind of a standard size for Boolean function, especially when used as coordinate function in Sboxes, then you have something that is basically in the same order of magnitude of the number of atoms in the observable universe. So we cannot do exhaustive search. And the case with the number of Sboxes is even worse because we have a vectorization of several Boolean functions. Okay, so do you have any questions up to now? Okay, then we start with introducing evolutionary algorithms that maybe you already saw, but let's say just to be sure that we are aligned on everything. So we start from the same point. So what is the reason why I called like these AI methods to design cryptographic primitives, where cryptographic primitives stand for Boolean functions and Sboxes? Well, the fact is that if you look into the traditional approach of constructing Boolean functions and Sboxes, usually mathematicians rely or derive algebraic construction. So they say, okay, I start, for example, with what are called, let's see. We have 2 options mainly. We have primary constructions and 2 secondary constructions. So not a lot of fantasy, but anyway. So what does it mean primary? It means here that we are starting from a different set of objects other than Boolean functions, for example, permutations. And then from here, let's say from scratch, we are generating a class of Boolean functions with a specified set of cryptographic properties. Secondary constructions, instead, we are not starting from scratch, but we are starting with Boolean functions already existing with certain properties. And then from there, we construct other functions with similar or better properties. So this is the usual way that it is done in the literature of Boolean functions and Sboxes, using algebraic constructions, so proving theorems about saying, okay, if you start from these conditions, then you will get like a bent function, you will get a function with best possible resiliency, and so on. On the other hand, so the problem with algebraic construction is that they are nice, of course, because they give you like a theoretical guarantee that you're getting what you're aiming for. The problem is that usually they give like a very restricted set of functions. So maybe you cannot expect to find a lot of diversity for these functions. And maybe you also want to include other optimization criteria, such as, for example, the implementation properties. So you want them also to be that can be implemented with very compact circuits in hardware, for example. So this is where AI is setting in a certain sense. So the idea is to use artificial intelligence methods to support the designer of a cipher to choose the right primitives that are satisfying, let's say, the best possible combination of cryptographic properties and, for example, also implementation properties. So by AI methods and models here, I mean something very specific. I mean optimization algorithms that are based not on exact methods, like, for example, simplex or integer linear programming, etc., but meta-heuristics. So in particular, evolutionary algorithms, swarm intelligence, simulated annealing, these kind of algorithms. Like, for example, here you see genetic programming. And also computational models that are studied in the realm of artificial intelligence, in particular cellular automata. Also neural networks, although to be honest, they have been used like in the past for these kind of things, but they turned out not to be that nice. So they just scrapped it. I think that they are still using them. I still saw some recent papers about using neural networks for generating pseudo-random numbers, so to use it directly as a pseudo-random generator. But you cannot tell like that this is a pseudo-random generator with strong cryptographic properties, because of the fact that neural networks have a lot of problems in being a black box model. It's difficult to understand what they are doing, etc. Cellular automata, on the other hand, are quite simple, and we will see how we can use them to define Sboxes this afternoon. But anyway, let's stick with the part of evolutionary algorithms and artificial intelligence method for combinatorial optimization. So the idea is that we have at our hand like a combinatorial optimization problem, which is defined by this map P, let's say, that is mapping, let's say, a set of problem instances to a family of solution spaces. And this, let's say, set S is also a finite set that is equipped with what is called a fitness function. So something that is able to tell us if we take a solution, how good it is to solve our optimization problem. And then the optimization goal can be either to minimize, so to take the argmin, so the argument, the candidate solution that is minimizing such a fitness function, or symmetrically to maximize it. So we take the argmax. And heuristic optimization algorithms, or meta-heuristics to be more correct, because heuristics are usually very specific for a single problem. Meta-heuristics instead are something more that can be applied to any combinatorial optimization algorithm problem in general. So the idea of meta-heuristics is to tweak, let's say in an iterative way, in an incremental way, a set or even just a single candidate solution, but in general a set of candidate solutions. And then we use this fitness function to drive the search, the optimization process. So to get to the minimum or the maximum, hopefully a global or a global minimum or a global maximum. Most likely it would be a local optimum, but maybe it will be good enough. So the first type of meta-heuristic that we will consider are genetic algorithms that are quite famous. So they were invented by John Holland back in the 70s. And they are based, let's say, on a loose inspiration to evolutionary, biological evolution, basically. So using the Darwinian principles of natural selection. The idea is that they evolve in parallel a population of candidate solutions to our combinatorial optimization problem. And this optimization is done in a black box way. So it means that we are only using the information given to us by the fitness function. We are not using something else like gradient or additional properties, structures from our search space. So just a function that is telling us, let's say, a number, saying how good it is, our function with respect to solving our solution to respect solving the combinatorial optimization problem. And then we use probabilistic operator to combine and evolve these solutions in a new generation, and then we iterate this. So usually when you're considering genetic algorithm, the classic encoding for candidate solutions is a fixed length bit string. And this is quite good for us because we are interested in bit strings with Boolean functions. So we can define a candidate solution in a genetic algorithm as the truth table, let's say, of a Boolean function. And if we consider what is called genetic programming, which is, let's say, a more recent meta-heuristic that was introduced by John Cosa in the end of the 80s or beginning of the 90s, don't remember exactly when. The idea here is that instead of evolving directly a solution. We are evolving a program that is solving our optimization problem. In our case, what is a program will be a Boolean function. The problem is that it won't be represented through a truth table, but it will be represented as a circuit, so as a very specific kind of program. In particular, genetic programming is encoding an individual by using a syntactic tree. So an example would be that the terminal nodes of this tree would be the input variables of our program or of our Boolean function. The internal nodes instead are operators that are combining what comes from below. So in our case, that would be Boolean operators like AND, XOR, NOT, OR, and so on. So here you have the example of this encoding that is computing the same Boolean function that we showed before in the previous slide. So we have 4 input variables. These will be the terminal nodes, so the leaves of our syntax tree. And then we combine them, the first 2 with an AND, and the second 2 with an XOR. And then we combine, again, these 2 results using an OR. And the result will be that particular algebraic expression that can be converted into synthesized into a truth table. Now, an evolutionary algorithm, be it genetic algorithm or genetic programming or differential evolution, there are many of them, usually follow this kind of loop. So we initialize our population of candidate solutions or candidate programs, as in genetic programming. And then we already start to evaluate the fitness function of this initial population. Then from there, we will apply some selection algorithm to say, okay, we just retain only the best solutions with respect to the fitness function, with some probability inside, so we don't do it in a deterministic way. Then we apply genetic operators, typically crossover and mutation, to produce new solutions from this highly fit initial solution. And after that, once we have our new generation, we again evaluate the fitness function for this new generation. And then we do some kind of replacement with the old population. So we find, let's say, a combination between new solutions and old solutions to retain. Then we decide whether to terminate or not. If we reach like a termination condition, like we did enough loops inside this diagram, then okay, we exit from our evolutionary algorithm and we give in output the best solution that we found so far. Otherwise, we go back for another round. Now we go into the details of each of these components. So selection, there are many ways to do that. Typically, the first method that was quite popular back in the day was roulette wheel selection, where basically we say that the probability of selecting an individual in the population is proportional to its fitness value. And you can, let's say, imagine like you have a roulette wheel where each individual is getting like a sector of this wheel that is proportional to its fitness. So those that have the highest possible fitness, like individual 1 in this example here, has a very high fitness, so it will get like 46.6% of this roulette wheel, so it will have a high probability of being selected. The other one will have something like 24.6% probability, and so on and so forth. And then basically you spin this wheel randomly, and then where it ends up, like the poles will be the individual that you select. However, this has some kind of problem, because basically it usually gives some biased selection in the end. Because the problem is that if you have, for example, a set of individuals that are very close to each other with very high fitness, then you lose diversity in your population very quickly. And this means that the genetic algorithm usually gets stuck in a local optimum very quickly. So a better selection operator is what is called the tournament selection, where we just discard this roulette wheel and we say, okay, I randomly sample t individuals, where t is a parameter that needs to be set in the beginning, and then we play a tournament with these t individuals. So we say, okay, we take the best one out of this tournament, or the best 2 if you want to apply also the crossover between two parents. And then you have also a difference between what is called generational breeding. So basically you draw as many pairs of individual as the population size in order to get keep the population size stable. Or otherwise you have the so-called steady state breeding. So at each iteration you just select a single pair and then you insert the outcome, the offspring of this pair inside the population. So for crossover instead, the basic idea is exploitation of the search space. So the idea is that we want to recombine what are called the genes of two parents, and the genes in our case will be bits, either 0 or 1. We want to combine them in such a way to find a new offspring, a child solution that is better, hopefully, than the parents. And there are many examples in genetic algorithms of crossover. So the classical one is what is called the one-point crossover. So between two parents strings, we say, okay, we select a random cutting point, for example, the third position in that example on the left, and then we exchange the values of the two parents to get two new children. So the first one will be done by copying, like in this example, the first 3 bits from the first parent, and the other 5 bits from the second parent. And vice versa, the second will be done by copying the first 3 from the second parent and the last 5 from the first parent. So it is exchanging. So for genetic programming instead, you have something called usually subtree crossover. So you have two trees that are representing two parent solutions. Then you select a random point inside this, a random node inside this tree, and then you swap the corresponding subtrees. In general, this crossover is called exploitation, or both subtree or one point, because usually you have, let's say, a geometric structure for your search space. So the idea is that you have something like, I don't know, a box or something like that is representing your whole search space. And then your solutions are represented as points inside this box. Okay, so in particular, the set of all your solutions in your population is also defining a hull or another bounding box, because you just take, let's say, those that are at the edges. Crossover operators like one point are called also geometric crossover, because basically if you select like these two parents for crossover, what you are doing with one point is to select something that is a convex combination between the two parents. So you are selecting something on the segment here, and this would be the children, for example, C1, and this would be the children C2. This doesn't seem obvious from that particular representation with bits, but if you use like a structure of a metric space by endowing it as a distance, the Hamming distance, then you get exactly this kind of structure. So this is why it is called exploitation, because basically we are exploiting the search space that has already been found by our current population. The problem is that this is not enough usually, because it means that the solutions are converging to a local optimum in that way. So we want to introduce also new genetic material, and this is done using mutation usually. So mutation is exploration, and in genetic algorithm basically it corresponds to random bit flips. So with a certain probability we are flipping each bit inside our genome of our solution. For genetic programming instead you have something usually called subtree mutation. So again you select with a certain probability a mutation point, and then from down there you derive a new random subtree. Finally, we have replacement and termination. So for replacement, when we said that we want to combine our new generation with the old one, usually you want to keep some kind of elitism criteria, in the sense that the best individuals from the previous generation is usually brought forward from to the next generation, because in this way you're not losing, let's say, the best local optimum that you found so far. Otherwise, you're always losing it. And then for termination, there are several criteria, as we already mentioned before. You can have like a budget of a number of fitness evaluations that you want to do. You want to say, okay, once we reach like a solutions diversity that is very low, so the solutions are very similar, it's useless to continue, so let's terminate like this. And you can have different other criteria like that. So the basic thing is that, like you see here in this webcomic from XKCD, usually genetic algorithms or evolutionary algorithms in general needs to be carefully set from the parameters point of view, like for example also the termination condition, because it takes time for them to find the hopefully the global optimum of a function that we are trying to optimize. So if you stop it too soon, then you would end up like the guys in this comic where they were using a genetic algorithm to decide the recipe for their canteen in their computer science department, and you have people with Cheerios that are seasoned with a shot of vermouth, or Skittles that are deep fried, and this kind of strange. I mean, it is just the genetic algorithm is still optimizing that function, so it means that it is in a certain sense finding optimal solution, but maybe those optimal solutions or local optima are not satisfying for us. So this is why you need to be careful in setting the termination criteria and also all the other parameters of evolutionary algorithm. And yeah, I think that at this point we can also finish. So we will start again from here in this afternoon.